So this topic is called Quantitative Chemistry, and to put it simply, this is where we use mathematical equations and mathematical calculations to work out things about chemical reactions. Now before we get to those chemical reactions and those calculations, there's a couple of key kind of concepts to cover. The first concept, the first kind of definition to look at is the idea of relative mass. And there are actually two different types of relative mass for us to look at. One is called relative atomic mass, and the other is called relative formula mass. And both of these concepts are very similar. They're just about us trying to work out how heavy different chemicals are, whether they're atoms or compounds. So we'll start with relative atomic mass, and it's easier to understand this if you look at an example. So if I take, for example, the carbon atom, I might want to know how heavy this carbon atom is. Now, most things you weigh in life, you normally weigh in grams, but that's not particularly practical in this case because atoms are very, very small. So you'd end up with a number with lots of zeros, and before you actually get into any proper numbers, it's very hard to keep track of that. So what chemists would do instead is to actually look at the mass of different atoms just compared to each other. So not worried about their actual mass in grams, just a comparison of their masses. So for example with carbon, if I look up its atomic number and mass number in the periodic table, I get an atomic number of 6 and a mass number of 12. So what chemists will use in this case is it will just say, let's not worry about the mass of this carbon atom in grams, let's just say its mass is 12 because its mass number is 12. And this idea of comparing different atoms to each other is easy to see if we look at another example. So if I look at magnesium, again, I'm not particularly interested in how heavy my magnesium atom is in grams, I just want to know how heavy it is compared to carbon. So if I look at its two numbers off the periodic table, magnesium has a mass number of 24. So basically it's got a mass twice as heavy as carbon has got. So again, I just compare one to the other. If carbon's got a mass of 12, I would say magnesium has a mass of 24. So that's what we mean by relative atomic mass. We're basically comparing all our atoms to each other, and the reference atom we use is carbon with a mass of 12. And that gives you this big fancy definition you have to learn off for what we mean by relative atomic mass. So the definition you have to learn is this. The relative atomic mass is the mass of an atom compared to that of the carbon-12 isotope, which has a mass of exactly 12. Now that's the definition. In terms of actually doing that in practice, like in a question might say, what is the relative atomic mass of, for example, lithium? All you would do in this question is that you look for lithium in your periodic table, you would look for its mass number, which is 7, and that would tell you that the relative atomic mass of lithium is just 7. Okay, moving on to relative formula mass, it's not very different to relative atomic mass. The only difference is that when we're looking at relative formula mass, we're looking at compounds rather than just elements. And the basic principle is if you're trying to work out a relative formula mass, you basically add up all the atomic masses of the different things in the formula and just combine them together. It's easiest to see this in an example. So for example, if I was looking at the formula sodium hydroxide, which is NaOH, the question might say, calculate the relative formula mass of sodium hydroxide. So I look at all the different atoms in the formula. So there's one sodium, one oxygen and one hydrogen. I have to look up their relative atomic masses, which is just the mass number in the periodic table, and add them together. So for sodium, its mass number is 23, oxygen is 16, and hydrogen is 1. In my calculator I would go, and I would add that all up, and I would get a number of 40. So for formulas, you just add up the individual atoms to get the relative formula mass. Now there's one type of calculation you might have to do in this topic which combines the ideas of relative atomic mass and relative formula mass, and this is where we try and work out the percentage mass of an element found within a compound. Now to do this calculation you need to use a formula which I write down here, which is the mass of the element in the compound divided by the RFM of the whole compound times by 100. As with every type of calculation, it makes more sense if you see it in an example. So an example question that might come up in the exam would be to calculate the percentage by mass of oxygen in the compound copper sulfate CaSO4. So you've got this formula here, copper with a sulfur and 4 oxygens. You want to work out of the total mass of that compound, the relative formula mass, how much of that comes from the oxygens. So we need two things for this. We need the mass of the element and also the RFM of the compound. Now the element in question is obviously oxygen, but we have to be careful here. There are 4 oxygens in the formula of copper sulfate. So therefore there's 4 oxygen atoms contributing to the mass of oxygen, so we need to times it together. So the mass of one oxygen, its RAM, is just 16 off its mass number in the periodic table. There's 4 of them, which gives you 16 times 4, which gives you 64 is the mass that comes from the oxygen. The RFM of the compound, we just look at the formula, it's got copper, which is 64 off the periodic table, sulphur's mass is 32, and again we've got 16 times 4 for those 4 oxygens. If I add that all up, I get 160. Now if I take these two numbers and plug them into my equation, the mass of the element in the compound is 64, divided by the RFM of the compound as a whole, which is 160, times by 100 to get a percentage, gives me an answer of 40%. Now the second main concept in this topic after relative mass is the mole. Now the mole has a bit of a reputation as being quite a difficult concept to understand in chemistry, but all you have to think about with it is it's just a word that represents a number. And we see that now in other cases in the language we use. For example, if you look at the word dozen, that is just a word that represents the number 12. The mole is no different to this. 1 mole is again just a word that represents a number, but the number is a little bit more ugly, or a little bit like less kind of round, like 12 is. It's 6.02 times 10 to the 23. Now the reason that we've picked this number to mean the mole is that it gives us quite a neat relationship between the mass in grams of a substance and also the relative atomic mass or relative formula mass of that substance. So for example, if you look at carbon, we'd worked out before by carbon, it's got a relative atomic mass of 12. If I just decided that because I like that number 12, because it's a relative atomic mass, and if I tried to weigh out in grams that same number, so in other words 12 grams of carbon, and then I was able to actually count up all the individual carbon atoms in 12 grams of carbon, what I would find is that I would have 6.02 times 10 to the 23 atoms of carbon. So in other words, if you weigh out in grams the number which represents the relative atomic mass, so 12 grams of carbon for its relative atomic mass of 12, you will always end up with 6.02 times 10 to the 23 atoms, and that's the same for every element in every compound, it's not just for carbon. So what scientists did is they took that number, 6.02 times 10 to the 23, and called it the mole. Now you might be thinking, well, why is that useful? It's useful because it gives us a key equation which we can use a lot in chemistry, which is that the number of moles of something is the same as the mass divided by the RFM. So to see that equation used in practice, a question that could come up in the exam is that you might have to calculate the number of moles in a certain amount of substance. So for example, here we're trying to work out the number of moles in 32 grams of water. So we use moles equals mass over RFM. The mass in the question is just 32 grams. The RFM, I need to look at the formula of water, which is H2O. In this case, there's 2 hydrogens and 1 oxygen, so I need to have 2 hydrogen masses, so it goes 1 plus 1 plus 16 equals 18. So the sum becomes 32 over 18. I'm actually going to change it slightly, I used the wrong number here. It's easier if we go for 36 grams, because 36 over 18 gives me a nice round number. That would give you 2 moles of H2O. Now this equation is very useful to us in a class of calculations known as reacting mass calculations, which we'll look at now. So in this type of calculation, you're given the mass of one thing within the chemical equation. So in this case, we got magnesium reactant with oxygen to make magnesium oxide, and we're told we got 16 grams of oxygen. Using that mass of one of the things in an equation, you have to work out the mass of one of the other things in the equation. So we're asked to work out how much magnesium oxide would you make. The easiest way I find to structure this question is to use a table. Now the first row of this table says ratio, and that gives us an idea of how much of one substance reacts with how much of another substance. So if I was to say this equation out loud, I would say that 2 magnesiums reacts with 1 oxygen to make 2 magnesium oxides. I'm just using the balancing numbers for that. So the ratio becomes 2 to 1 to 2. In terms of the mass, I only know one mass at the start. I know I've got 16 grams of oxygen. And I know that I'm trying to work out the mass of magnesium oxide at the end. That's what the question says I have to do. So because I've only got oxygen and magnesium oxide in this question, I can ignore magnesium just because it's not required in this question. It could have been phrased differently that I would need to look at it, but in this case I don't, so I can get rid of it. The general idea here is that I want to work out from the mass of oxygen to moles of oxygen. I want to use my ratio to work out the moles of magnesium oxide, and then go from moles back to mass to get the final answer. So to work out moles of something, I need to use my key equation, which is moles equals mass over RFM. So to work out the moles of oxygen, I obviously need the RFM. If I look at the formula of oxygen, it's O2, it's diatomic, therefore there's 2 oxygens bonded together. Therefore it's 16 plus 16, which is an RFM of 32. To work out the moles, I need to do 16 divided by 32, which I can do in my calculator in my head, it comes out as 0.5 moles. This is where the ratio comes in. I know that if I had one oxygen, it would make 2 magnesium oxides, so that's a 1-2 ratio. So if I kind of scale that up, if I've got 0.5 moles of oxygen, I use that 1-2 ratio, I times it by 2, I'm going to make 1.0 moles of magnesium oxide. So I know the number of moles of the product I'm going to make now. I need to work out how much that is in mass. So to do that, I need to do a little rearrangement. I want to work out mass. I've got moles and I can work out RFM. So I use mass equals moles times RFM. The RFM of magnesium oxide, I need to be careful here. I don't include this big 2 here because it's just a balancing number for the ratio. That seems a bit confusing because I used it here, but remember, that's a little 2, that's part of the formula of oxygen. The formula of magnesium oxide is just MgO. So mass of magnesium is 24, mass of oxygen is 16, 24 plus 16 is 40. So to work out the mass, I do 1 mole times by the RFM 40, which gives me 40 grams of magnesium oxide, which is the answer to the question. Now there is one slightly harder style of calculation which is very similar. It's known as a limiting reactance question. So this question looks very similar to one we did before, but it's got one crucial difference. Again, I have to work out the mass of magnesium oxide, but in this case, instead of just having the mass of one reactant, 16 grams of oxygen, I've got a mass for both reactants, so I've got 2.4 grams of magnesium. So that's how you spot this as a harder style question. But what I do is I just kind of treat the 2 reactants the same at the start anyway. So I can fill in my ratio, it's still 2 to 1 to 2. But the difference here again is I've got 2 masses. I've got 2.4 grams of magnesium, and I've also got 16 grams of oxygen. So where I might start is I just treat it the same as I did before. I'm going to work out the moles for both of the reactants. So I'm going to use moles equals mass divided by RFM. The RFM of magnesium, remember I ignore the big 2 because it's just for balancing for the ratio, it's just 24. So 2.4 divided by 24 is 0.1 moles. The RFM of oxygen we did before, that little 2 is part of the formula, so I include it. It's 16 plus 16, which is 32. 16 divided by 32 is 0.5 moles. Now here's the tricky bit of the question. I need to work out which one of these 2 I'm going to use for the ratio to work out the moles of magnesium oxide, the missing column there. So what I need to do is kind of compare them to each other. One is going to run out first because there's less of it. And when that one runs out, that's going to stop the reaction and the other one's going to be left over. And once the reaction stops, you've made all of magnesium oxide you possibly can make and you can't make any more. So to work out how much magnesium oxide is going to be made here, I need to identify which reactant will run out first. So if I look at magnesium first and look at the ratio, if I have 0.1 moles of magnesium, if that reacts fully, it's a 2 to 1 ratio, magnesium to oxygen, that would therefore react with 0.05 moles of oxygen, just using that ratio. So if I think about how much oxygen I actually have, I have 0.5 moles of it, that's 10 times as much as I need. So therefore I've got more than enough oxygen to fully react all the magnesium. However, if I do it backwards, the other way, just to check, if I wanted to fully react 0.5 moles of oxygen, 1 to 2 ratio, I would need 1.0 moles of magnesium to get to fully react. Do I have that? No, I don't. I don't have enough. I only have 0.1 moles. So again, magnesium's running out first. I've got lots of oxygen left over. So if magnesium runs out first, it's going to be determining how much magnesium oxide I'm going to make here. So I use it for the ratio. So I ignore the oxygen out because it's going to be left over. And I look at the ratio between magnesium and magnesium oxide. It's a 2 to 2 ratio. Therefore, 0.1 moles of magnesium will be the same. It'll be 0.1 moles of magnesium oxide. And at that point, it's just like a normal question. So I look at my moles and need to convert back into mass. So I need to use moles times RFM. The RFM is 40, like we worked out before, 24 plus 16. So 0.1 times 40 gives me a final answer of 4 grams in this case. The final section of this topic is something called percentage yield. And whenever we see the word yield in chemistry, it just means how much of something do you make in grams. There's 2 types of yield you have to be aware of. Theoretical yield and actual yield, and they each have their own definition. The theoretical yield is the maximum mass of product that you could obtain in a reaction. Basically, that's what you'd work out in a calculation as being like the ideal full amount of something you possibly could make. The actual yield is the real life one, so it's the actual mass of product you'd obtain in a real life experiment, and in general the actual yield will be lower than the theoretical yield because a reaction never goes perfectly. You'll never make the exact correct amount that you're meant to make according to your calculation. So you might have to do a little numerical calculation. It's quite simple to work out the percentage yield you get in a real life experiment. And that is that the percentage yield equals the actual yield divided by theoretical yield. So if we look at an example, if we look back to this first reacting mass question we did, here we worked out we should make 40 grams of magnesium oxide in this experiment. Let's just say that in the question it says this experiment was carried out in real life and they only obtained 30 grams of magnesium oxide. So in this case, the actual yield would be 30 grams because that was what was obtained in real life. The theoretical yield will be 40 grams because that's what the calculation said you should have made. So the calculation just becomes 30 divided by 30 times by 100 equals 75%. Now in real life you will never obtain 100% yield because generally something will go wrong that means your reaction doesn't actually give you 100%. And you need to know a couple of reasons for that taking place. So some potential reasons are that some product might be lost when you're taking your reaction out of its beaker. Another reason might be that you get some side reactions, it means you get some undesired products. And the final reason might be that the reaction doesn't actually go all the way to completion, so not all of the reactants turn into products.